The reason we have to cover state diagrams and AOI logic before we do anything else is because you need this for lab 4, the lab next week. And we're having a quiz 2 today on master and slave DFF. I'm going to give you a really quick review on that pretty soon. And there will be a homework due next Wednesday. Homework 4 will be due next Wednesday. And break on October the 1st. You know that, right? It's a long weekend. Friday is the 1st. Oh, I do have 3 days break because the ABAT review is starting on Monday. So I don't have, goodness. Been working on that for, since January this year, and I spent 4 weeks in the summer in May. I didn't do anything in May, just totally writing on the report. It's an assessment report for the department, 400 pages. It's done. And okay, so you know what's going to happen next week, right? So Monday, Wednesday, 2 lectures, Tuesday's a lab, and a quiz Wednesday, which will be the similar problems on homework 4. If you do homework 4 and turn it in on Wednesday next week, it'll be fine, right? So the quiz. Thank you. Do we have a homework due today? Do we? Oh yeah, we do have one. Just turn it in, please. It's a rising edge trigger master slave D flip-flop. So the schematic should show up in your mind, right? What that looks like. You have 2 D flip-flops, 2 stages. A master stage and slave stage. And it's rising edge trigger, which means the inverter, the clock has to be inverted, and then, no, the clock is being inverted for the first stage, and the clock is directly sent to the second stage to trigger that change for the Q, right? So here's must be something like I want to clarify on. So at the very beginning, it doesn't matter what the initial value for D is, or the initial value for Q is. You can assume the initial value here for, since you are being asked to draw the signal at Q. So if you assume the initial value for Q is 0, which is fine, right? Then it's a rising edge triggered. So for example, you start drawing that. So Q started with 0 and lasts for a while. So here's a falling edge for the clock. So this falling edge is going to sample a 0 and being stored in the middle stage, in the middle, right? And then it's rising edge trigger. So whenever you see a rising edge, it's going to send whatever being sampled here at the falling edge and send it to Q. So here should be 0. Still 0. If you start the signal with 0, then this rising edge will give you a 0 as well. It's not changing that result. And then this falling edge, it's going to sample this one and send it to Q as this rising edge. So until here, it was 0. And now after that, it's going to be a 1. It's going to be a 1. and this falling edge is going to sample this 1, and rising edge will trigger it. It's still 1. It's not going to change it, right? Is that clear? Any questions? I want to go through all of these, right? Just give you some hint on this. Okay, doable. So now let's come back to the AOI logic, since that's what is on the homework for, and due next Wednesday. Okay. So first, we started looking at the logic expression like this: y equals to a not or bc. Last time we just did it, right, on Monday. So the workflow to design the Cmos-based circuit, the starting point is, if you do not have a bar on the top, you want to create a bar. And if there's no bars, you just want to add 2 bars on it, so it's still the same signal. I will just do it very quickly, since we just did it on Monday. So you probably have the solution on your notes. So the reason we need a bar on the top is because whenever you are designing the AOI logic or complex, it's called complex CMOS circuit, so they are not so the logic expression is not being implemented by individual logic gates. If you do this, if you just want to design a digital circuit out of this guy, it's very simple. We have done that in logic for many times, right? So just have an A, B, C, for example, this is A naught, and B, C are being ANDed and being ORed with A naught, so we can get the result very easily. The cons for this one is it's just taking a lot of space, right? So we want to use complex CMOS circuit. And how do we get this one? We need this AOI logic. It's an AND OR inverter logic. Okay, to form the circuit can do the same job as this one, which takes less space. So we want to start from here, so we want to reserve a bar on the top for the overall expression. So we start from here is the De Morgan's law, just apply De Morgan's law, and this equals to, so De Morgan's law, if we want to make it simple, it's just to split the bar and change the sign. So split the bar first, split the bar, change the sign. So split the bar, you are getting A naught naught and BC naught. Still reserve the top bar on the top, right? But split the bar, the second bar, and change the sign. And this equals to A and BC. And this is also A and B naught or C naught, naught. So now we have the structure ready for that complex CMOS circuit. So when you are converting this one to the CMOS circuit, always think about the NAND gate and NOR gate, because we know we have proved that you need a CMOS circuit instead of just NMOS or PMOS. So C stands for complementary, because PMOSs are good at passing ones. NMOSs are good at passing zeros. That's why I need a complementary MOSFETs, right? And when you are thinking about the circuit structure for this one, just always have that image, the picture of NAND gate and NOR gates in your mind. Like NAND gates, you have parallel PMOSs on the top, and NMOSs in series at the bottom, right? For NOR gate, you have PMOSs in series on the top, and NMOSs in parallel at the bottom. A or B, A nor B, A NAND B. Okay, so for OR logic below the bar. For the OR logic, you need two Cmoses in series on the top and two NMOSes in parallel at the bottom. Why? We can demonstrate it. We can just give examples for A and B's and demonstrate it, right? But you don't have to think through this every time. This is the conclusion. Just memorize it. If you want to demonstrate it, let's do it. It takes time. Every time you demonstrate it, you have to give examples for 1 and zeros. All right, to demonstrate the truth table, to prove the truth table. But we don't have to do this in the future since we know it's going to work. Okay, for an OR operator below the bar, you need two Cmoses in series and two NMOSes in parallel at the bottom. And for AND logic below the bar, you need two Cmoses in parallel and two NMOSes in series. Since this applies to any AOI logic in the logic expression. So for this one, you have, if you treat this guy as a black box, right? You have an AND operator below the bar, so you must need Cmoses in parallel, NMOSes in series. So that's the structure for these two, right? So you need A and something, right, in parallel, and also A and something in series. And now you can look at B naught and C naught. It's an OR logic. It's and below the bar, it's an OR logic. So the Cmoses needs to be in series. Think about the NOR gate. And you need two Cmoses in parallel, two NMOSes in parallel, because the NOR gate has two NMOSes in parallel at the bottom. Oh, sorry, NMOS. And here should be a OR in here. So now a quick question. Can I swap the signal line? For example, I just labeled here as B naught. No, this is designed for A. It has to be A. So the signal A has to be shorted to this Cmos. What about this Cmos? And also A as well. What about these two? Are these two interchangeable? So B naught, C naught, or C naught, B naught, does that matter? It doesn't matter. What about these two? Doesn't matter as well. And that's a complex CMOS circuit for this logic. So if you want to prove it, let's see. Give some examples. If A is 1, B naught is 0, C naught is 0, and naught. So what is the result? And now let's look at the circuit, see if that's true. Okay. If A is 1, the PMOS is shut off. So there's no pathway to the VDD. And B naught, C naught, they are both zeros. So you got a pathway to VDD. And keep in mind, you got a bar here. Wait. B naught, C naught are zeros. If this is 1, 0, 0, it should be 1. I'm just treating B naught C naught as one entity. So what's wrong with this? So C A. Oh, this is a that's a non-logic, so these two should be in series, and this NOR should be in parallel, and that is correct. Zero, these are off. Huh? No, but the thing is, if you have these two on, to be on, is A is 1. No, this is 0, right? And 1, 0 not is 1. Yeah, you're right. So I don't know why, just looking at this one, I was thinking this is the entire thing is 0 here. Because I saw this is 1, whatever. So it's 1, and verified, it works. This is for this logic. So let's get another example here. So one more question, is there another way to do this? Instead of just put everything in one complex Cmos circuit? Yeah, for this part, you can directly just build this part and then invert it and put an inverter just afterward, directly after that circuit, right? You just have more transistors. This one, you have 6 transistors in total. And now let's just build this one for now. Let's just look at what that looks like, how that looks like. So don't just ignore the bar on the top first. This is where I'm going to invert it eventually. But just look at this part. It's a NOR gate, right? It's a NOR gate, then you need an A bar on the top and NAND gate, these two guys in parallel. And BC is a NOR logic, so it should be in parallel at the bottom. And these two should be in series. And this is A naught, this is B, this is C, and this is A naught, B, C. Okay, so what's the result here though? Right, it's this part. But if I want to recover this logic, you still need an inverter to invert it. And now it is A NA or BC. So compared to this one, this has two more transistors. Okay. Another example. Y equals to A or B not C or CD. Split the bar, change the sign. Right? And then am I doing this correctly? I should actually take C out first at the very beginning. That'll make things easier, I think. Let's cover C. So not going to use this one anymore. And just verify it before we make any mistakes. Yeah, that's right. And then do it again. See if I make any mistakes. I'm a different result here. No problem here. No problem here. Problem here. Found. Right? And now let's do this. So first, NAND gate is a NAND operator, so it should be in parallel. And in parallel, then these two should be in series, and this should be in parallel. So you are getting B and D not in parallel, and in series with C not, and in parallel with everything. So this is A not, this is B, D not, and this is C not. Now look at Nmoses. So A and everything are in series actually. So this will be A not, and everything else here should be in series. And these two are in series and in parallel with this guy. So you are getting this one in series and one in parallel with these ones. So B, D not, and C not. Let's give one example, see if that's correct. 1, 0, 1, 0, for example, right? 0 here, 0 here, still 0, 0 and 1, 0, inverted, you're getting 1, right? So A naught is 1, so A naught B is 0, D naught is 1, C naught is 0. We got a pathway to pull it up to VDD. So got a 1, but still have to block whatever underneath here. So 1 here, B is 0, D naught is 1, C naught is 0. It's blocked. These two are blocking the pathway to the ground. Although this is on, it's not making sense. It's not going to make it work. Very quick verification. If you want to explore all the combinations, you can just do it. You're going to have 16 combinations for the inputs, and it's going to work. So if you know it's going to work, just directly use it. That's a conclusion. Okay. And that's a circuit for this one. See if I have more examples. What about XOR? The XOR gate. So what's the XOR logic first? AB. It's A XOR B. Goes to A not B or A B not. Let's say I can design a circuit. Right, so A not B, A B not, and then OR them. That's XOR logic. There's just too many transistors in there, right? You want to use CMOS, complex CMOS logic circuits, or through the AOI logic. And we know that the XOR logic is inverted from the XNOR logic, which is, this is a conclusion from logic, from 241, right? We can demonstrate later, but just keep in mind this, they are equal to each other. And XNOR is this. So we directly have something below the bar. Okay. And now we can start drawing that complex CMOS circuit. AB, parallel PMOS, and in series. So two pairs of parallel PMOSes in series. series NMOSes, and parallel NMOSes. Okay. Only 8 transistors. Making sense? You do need some practice on this. That's why I have the homework assignments, homework 4, due next Wednesday. A quiz on this due next. So there will be a quiz on AOI and complex circuits next Wednesday as well. Same topic. So practice on that through the homework 4. This is very helpful when you are hand drawing the layout, which has a lot of transistors in there. It's not just like an inverter. You can directly draw it very easily. But whenever it scales up, you need this one to help you to draw it, to design it first. And we use this symbol for PMOS and this as NMOS. So these are the contact from the diffusion to the metal layer, and that's the gate, and that's the channel. Same for this one. So if I draw this, and this, it's the same as or equivalent to a PMOS. If I do this, it's the same as NMOS. So if I got 3 NMOSes in series, you can draw it as, that's wrong, that's PMOS, right? NMOS. So 3 NMOSes are being shorted together. And you can see there are metal, 2 metal contacts. It's just redundant. So you can simplify this layout into this version. Right? Just ignore these 2 contacts. And you can simplify this further if you are not using the gate in the middle. For example, you are not sending any signal to the gate here. You can even ignore that one. So it end up with this. It's fine to have a gate in there, or you can ignore it, doesn't matter. So parallel, if you have 2 NMOSes in parallel, short these 2 guys together, and you get a pin here, X, and here's Y, 2 gates. So these 2 NMOSes are in parallel. They're in parallel because it's the same as this, right? If you draw it in this way. same, right? So two NMOS is in parallel. Or I can just draw this. No difference, right? All the same circuit. All the same. So if you draw the diagram, the state diagram from this parallel NMOS structure, it looks like this. Is that correct? These are the two gates. They are in parallel because if you feed a signal into X, it's going to be split in two directions and go through the channel of the two NMOSes and merge to this point. So that's why they are in parallel. Make sense? Okay. Let's do the quiz. I mean, for most of you guys, it probably will take shorter time to get it done, but I would like to give you guys 20 minutes to work on it. You can turn in earlier if you like. So for the people who came over late, just let you know, just be fire, okay? So this is a master slave D flip-flop. It's a rising edge trigger. Have two stages. So two D flip-flops, right? Put it together. It's a rising edge trigger. So it samples data at the falling edge and triggers the change to Q at the rising edge. And it can assume the beginning, at the very beginning. It can be high, can be low, but if you assume the Q, if you are drawing a Q signal just underneath it, right? So you can assume Q to be 0 at the very beginning, which is fine. If you want to assume Q to be high, which is fine too. You just need to get the correct signals for the following rising edges. Okay.